In this video, I will discuss some JEE Main PYQs from the topic Electrostatics. These questions have appeared in the year 2025. Timestamps are given in the description box. You can watch parts of video if you're running short of time. This is the first question. A particle of mass m and charge q is fastened to one end A of a massless string having equilibrium length L, whose other end is fixed at point O. The whole system is placed on a frictionless horizontal plane and is initially at rest. If uniform electric field is switched on along the direction as shown in the figure, then the sphere of the particle when it crosses the x-axis is. You can pause and run this question. So this is the x-axis, this is the y-axis. So this end of the string is fixed, and the other end there is a charge of mass m and charge value is q, and this connected by a string of length L. So this electric field will exert a force on this charge of value qd, and there is a tension in the string. So this thing will start moving like this in a circle because the string length is fixed. And here when it comes, it will have some velocity v. The initial velocity is 0, starting from rest. So you have to find this speed v. So this can be solved by work energy theorem. Initial energy of the charge equal to the final energy, and work is done on this charge by this electric field. So work done on the charge will add to the initial energy to be the final energy. And work done is F dot ds. This will be integrated. So this F into ds into cos theta. Force is uniform force. It's always qt, and the direction also towards the x-axis. So force is uniform. So force will come out into ds cos theta for this entire path, and ds cos theta is nothing but component of the force along the component of the displacement along the direction of the force. So which is the x displacement. So this is nothing but dx, and the total displacement is from here to here. So this is the total displacement, which can represent as x, and that x is nothing but this length minus this length, that is L minus this length is L cos 60. So initial energy is 0 because kinetic energy is 0 and there is no other form of energy, and the work done is force q into E into L into 1 minus cos 60 is half, because cos 60 is half. That's equal to final energy, which is the kinetic energy, half m velocity square. So half and half cancel. So velocity is QEL by m square root. Three is the correct option. So this is what I explained here. This is work energy theorem. Initial energy equal to final energy, and work done on the system will add to the initial energy to match with the final energy. So work done on the system is a force, external force acting on which is the electric field into the charge, into the total displacement. It's a uniform force, and the total displacement is L minus L cos 60. And final energy is the kinetic energy, it's half mv square. From this we get the velocity as this one. Next question. An electric dipole is placed at a distance of 2 cm from an infinite plane sheet having positive charge density sigma naught. Choose the correct option from the following. Option 1, torque on the dipole is 0. Net force is directed away from the sheet. 2, torque on the dipole is 0 and net force is acting towards the sheet. 3, potential energy of the dipole is minimum and torque is 0. 4, potential energy and torque both are maximum. Infinite sheet. So the electric field is uniform everywhere and that value is sigma by 2 epsilon naught. This can be applied by applying Gauss law to a small cylindrical pill box here. So we'll use this result. So the force on this charge is in this direction, Q into the electric field, which is sigma by 2 epsilon naught. On this minus charge will be attractive force towards this positive plate of value Q into E, or you can say minus Q, because the direction is towards the plate. So the net force on this system for the dipole is 0, because the two forces are equal in value on opposite direction, and the torque, net torque above this middle point will rotate about the middle point by symmetry. So the force, the torque due to this force is 0, because the distance of the force from the point is 0. So the net torque, even the individual torques are 0. And if I disturb this thing from this position like this, so plus Q comes here and minus Q here. So there is a force like this, will try to bring it back to the equilibrium position. So this is a stable equilibrium position. So stable equilibrium position means the corresponding potential energy is minimum. Another way to figure out the energy of the system is minimum is using the formula for the potential energy, which is minus P dot E. So this will have a cos theta variation. P is fixed, E is fixed. So cos theta will have a variation between minus 1 and plus 1. So when this is plus 1, or when cos theta is plus 1, the potential will be minimum. So in this particular configuration, P is from minus Q to plus Q. So P is like this. Electric field is also towards right. So P dot E is that cos theta is plus 1. So this is minimum energy configuration. So it is stable configuration. So option C is the potential energy of the dipole is minimum and torque is 0. So C is the correct option. C is the correct answer. So this is what I explained here. Infinite sheet. So the electric field is E, uniform throughout, and that value is sigma by 2 epsilon naught. And the force on this plus charge is Q into E towards right, and force on this minus Q is Q into E towards the plate, because there will be attractive force between the negative charge and the positive charge, and there will be a repulsive force between this positive charge and this positive plate. So net force is 0, and the torque, the individual torques are 0, because the force is passing through the axis of rotation. So torque is force in the perpendicular distance. Here the distance of the force from the axis of rotation is 0. So net torque is 0. And the equilibrium is stable equilibrium, because if it displaces this thing a little bit, it will try to come back. So that means potential is minimum. Another way to figure out the energy is minimum is from the formula potential is minus P dot E. So this will be minimum, P dot E is positive and maximum. So that is when theta is 0. So here theta is 0 because P is towards right, E is also towards right. So option 3 is the correct answer. Next question. In the first configuration 1, as shown in the figure, 4 identical charges Q0 are kept at the corners A, B, C, and D of square of side length A. In second configuration 2, same charges are shifted to midpoints G, E, H, F of the square. If K equal to 1 by 4 pi epsilon naught, the difference in the potential energies of the configuration 2 and 1 is given by. So here there are set of 4 charges. So the potential energy of the system is sum of all the interactions one can have. So here there are 4 interactions along the side and 2 diagonal interactions. So it's U1 plus U2, so not U4, and then U5 plus U6. And U1, U2, U3, U4 are same. The value is same because U is K into product of the charges, which is Q0 square, by the distance square, which is the side. Between this and this interaction, this is the value of the. So all 4 are same. So this into 4 times. This Q1 plus Q2, Q3 up to Q4. And Q5 and Q6 are same. The interaction energy is Q into Q0 square. But the distance is not distance square, it is distance. Energy dimension is same as the work done, and force is Q by R square, and energy or the work done is force into the distance. So it's Q by R dimension. So the formula should have distance in the denominator, not distance square. Distance square is force. And here the distance between the along the diagonal is root 2 times E. So K Q0 square by E into 4 plus 1 by root 2. So this is for the configuration 1. First configuration. Second configuration again it's a square, but just the side of the square will become this one. And this value is, this is A by 2, this is A by 2. So A by 2 into root 2. So it's A by, so the size of the square has decreased by a factor 1 by root 2. So potential of the second configuration is replace A by root 2. So it will go up by a factor root 2. So root 2 times so the difference in the energies, let me call it delta U. So it will be root 2 times root 2 minus 1 into this one. There is a small mistake here. So this is U5 and then U6. So into 2 I should do. So this will become 4 plus root 2. So this factor is there. And then the numerical thing is root 2 4 times and then minus 1. So it will be 3 root 2. Okay, this into this is 3 root 2 and then minus 4 and then plus 2. So it's minus 2. So option 4. 4 is the correct answer. So this is what I done here. For the first coefficient, the energy of the system is energy of all the 6 interactions, 4 along the side interactions, and 2 diagonals. So it's 4 times U1 and 2 times U5. 4 times U1 is the side interaction, which is K into charge square, product of the charges by the distance. And then 2 into U5 is product of the charges is Q naught square, and the distance is A root 2. So this will be this one. In the second case, the side will become A by 2 root 2, so it's A by root 2. So if we replace A by root 2, energy of the system of the second configuration will get. So the change in energy is this minus this, so it's root 2 times minus 1 into this one, select this one. This is the next question. Consider a circular group that is uniformly charged and has a radius A root 2. Find the position along the positive z-axis of the Cartesian coordinate system where the electric field is maximum if the ring was assumed to be in the xy plane. You can pause and run this question. So the ring is like this, and this is the axis of the ring, which is the z-axis. So this is x, and y-axis is out of the plane of this board, xy plane. So here we can use the formula straight away. If you remember the formula for the electric field along the z-axis, it's k into the total charge of the ring q into 1 by r square will take the form distance by distance cube. 1 by r square dimensionally it's same as distance by distance cube. So the numerical distance is the, suppose I want to find the electric field at this particular distance, say z. The distance in the numerator is the axial distance, which is z, and this denominator is the hypotenuse distance, which is square root of r square plus z square root into that cube. So it will become 3 by 2. So this is the formula for the electric field along the axis of the ring, which is uniformly charged. So we can certainly use this formula. So this is a function of z. For z equal to 0, the value is 0, and z equal to infinity, then also this value is 0. So somewhere in between, the electric field should peak. To find that, you have to maximize this function, let me call it f of z, as a function of z. So to do that, we can use the calculus f dash z. It's u by v form. So it is equal to v, which is this raised to the power 3 by 2. The derivative of u is 1. Minus u into derivative of this with respect to z, that is 3 by 2, this is raised to the power half, into derivative of this with respect to z, which is 2z, by denominator, which is v square, where v is the denominator. This should be equal to 0, so numerator has to be 0. So from this I'll get 3 root can be cancelled, equal to this, which is r square plus z square. So 2z square r square, so z equal to r by root 2. So distance of 1 by root 2 times the radius of this ring, the field will be maximum. So here the radius of the ring is a root 2. So 1 by root of the radius is e. So distance of a from the axis of the ring, along the axis of the ring, the electric field will be maximum, which is option 3. 3 is the correct answer. So this formula which are used in this question, this can be derived using Coulomb's law. So to do that, we will take a pair of elements. Then the electric field due to this upper one will be like this, and to this diametrically opposite element will be like this. So the net electric field will be along the axis because the perpendicular components will cancel. So all the elements will contribute, only the axial component will contribute, the perpendicular components will cancel each other. So the electric field due to the small element here is K into the small charge dq by distance, which is r square, and the direction is, we are taking this along this one, but only the axial component will contribute. The axial component is this cos theta, because this angle is theta, this angle is theta. So cos theta is the axial component which will add up. So r square in terms of r and x is this one. Okay, the axis of the ring is along the x axis, and then cos theta is x by hypotenuse, this one. So the total electric field is the total charge we have to put, because all the elements, their axial component will add up. So the total electric field will be just this charges will sum up to give the capital Q. So it's 1 by 4 pi epsilon r Q into distance by distance Q. Numerator distance is the axial distance, and the denominator distance is the hypotenuse distance. So here in this question, the axis of the ring is the z-axis. So the electric field on the z-axis is K into Q into distance by distance Q. Numerator distance is the axial distance, denominator distance is the hypotenuse. So this electric field is a function of z. It will have maximum value somewhere in between. So this was the form u by v. So the derivative is v into derivative of u minus u into derivative of v. So this has to be 0, so numerator has to be 0. From that, the z value is radius divided by root 2 for the electric field to be maximum. This is the next question. A small bob of mass 100 milligram and charge less than microcoulombs is connected to an insulating string of length 1 meter. It is brought near to an infinitely non-conducting sheet of charge density sigma, as shown in the figure. With the string subtends an angle 45 degrees with the sheet at equilibrium, the charge density of the sheet will be. You can pause under this question. The forces acting on this charge are its weight mg, and because of this infinite sheet, electric field everywhere is uniform, and the uniform electric field is sigma by 2 epsilon naught. So because of that, there will be a force on this positive charge in the direction of the electric field of value qt, and there is a tension of the string. So vertical balance, this is 45 degrees. So t by root 2 and t by root 2 in the horizontal and vertical directions. So t by root 2 in the vertical direction is balanced by the weight, and t by root 2 in the horizontal direction is balanced by the electrical force. So since this left hand side is equal, right hand side should be equal. So mg equal to q into e. We have to find sigma. So electric field is sigma by 2 epsilon naught. So mass is 100 milligram. So milli to gram is 10 to the minus, and then gram to kg is another 10 to the minus 3. Into g is 10 into 2 epsilon naught. Epsilon naught is 8.85 into 10 to the minus 12 divided by q. Q is 10 micro, so this is 10 to the minus 5 coulombs. So this is 10 to the minus 5 this will become 10 raised to minus 1, so we'll cancel out 110. Okay, so 2 times this one is 16, 17, 17.7 into 10 raised to minus 11. Okay, so in terms of nano, it will be 10 raised to minus 2, so 0.177 nanocoulombs. Mass is 100 milligram, right? So there is 100 here. So this is 10 raised to 10. So it's 1.77 nanocoulombs. Mass is 100 milligram. So 100 milli to gram is 10 raised to minus 3. And then gram to kg is another 10 raised to minus 3. So option 4. 4 is the correct answer. So this is what I explained here. This is an infinite sheet. So electric field is uniform everywhere, and that value is sigma by 2 epsilon naught. So in the vertical direction, the force's weight mg is balanced with the tension component, which is T by root 2. Horizontal direction, Q is T by root 2. So these two are equal. So these two should be equal. So Q into sigma by 2 epsilon naught is mg. So from this, putting the values of the different quantities given, the correct answer is 4.